Now, our next presenter has presented at SAE. Right, Jeff? Thank you. I can't tell you how long Jeff has been looking forward to this presentation. Actually, I can. 9:30 this morning when we told him he had to do it. So, actually, coming to the stage now, I'd like to welcome up not just an all-around great guy, but somebody that I really rely on to make sure the NVH portion of our business runs smoothly. Jeff Hodgkins comes to us from Toyota. We've been a pleasure to have him now for a number of years with us on the team, but he's going to come up and talk to you about how we can really experience the CAE portion in the NVH simulator. So Jeff Hodgkins, the stage is yours.
So again, my name is Jeff Hodgkins from VI Grade, and I'm basically going to be going over a presentation on experiencing noise and vibration from CAE simulations in an interactive multi-attribute driving simulator. Working title, How I Spent My Summer Vacation. Don't let the title fool you. This is really boring stuff. So this has been covered several times today, but we've got several current NVH challenges that we have to deal with. Of course, we've got electric vehicles, so either you're retrofitting a current internal combustion engine platform or developing a brand new platform to support this type of electric powertrain. Hybrid vehicles, best of both worlds. You have to deal with the noise from an internal combustion engine and the noise from an electric motor. Autonomous vehicles, this is an interesting one with the case of now the main occupant may not be sitting in the driver's seat anymore. So now we have to rethink targets, whether they're in the front or the rear of the vehicle. And now that the occupant doesn't have to worry about driving, they have a little bit more mental bandwidth to focus on other sounds that could be occurring in the cabin. Vehicle lightweighting, we're all familiar with that one. And development time and cost. So as we're pushing towards trying to reduce prototypes and trying to shorten that development schedule, the normal approach of developing a prototype and evaluating it well after tooling starts to become a very difficult approach. So this is where an increased reliance on simulation is needed. We can now try to do some early feasibility studies that decide future development paths, and we can facilitate a development decision for subjective experience, where now we have compact simulators that can provide an immersive vibroacoustic environment to answer some of the questions of, does it sound good? Is it better than this? Or just straight up, what does it sound like? We're all familiar with the standard vehicle development schedule. A lot of the early target setting is done very early in the development stage. There's some design iterations that occur, but in the end, the final evaluation isn't done until a prototype well after tooling. With the idea of virtual prototypes, we want to be able to pull all of that development very far forward to be able to iterate and work on these virtual prototypes while still not just looking at graphs on a plot, but being able to subjectively evaluate that vibroacoustic response. As Dave presented, we've got several frequency ranges that we tend to focus on. Now, of course, current acoustic simulators can basically simulate a range of 20 hertz to 20 kilohertz. And then also there is the tactile vibration range that's needed up to about 20 to 200 hertz. Now, in this overlapped area, the two of them work hand in hand. So there is basically a interaction between the two that can change an operator's perspective on how something sounds or how a vibration feels because of that contextual combination of those two. So this is where the introduction of a multi-sensory NVH simulator, or just the compact NVH simulator, comes into play. It's basically a driver-in-the-loop simulator that provides immersive sound, vibration, and visuals. It is a multiple degree of freedom, calibrated, synchronized sound and vibration tool at primary driver touch points. So we've got stereo sound, and we've got various shakers at heel, seat, steering. So now we'll talk about what I worked on. So in the NVH simulator, we have the ability to create CAE, models, we have the ability to create test data models. In a lot of cases, like Dave presented earlier, we can do a hybrid approach where we can combine CAE data from models like an Altair HyperWorks, and we can combine on-road test data to provide that supplemental vibration or acoustics above the frequency range that the CAE model can run. So that is basically what I did for a study here. So basically I took a CAE model, which was a finite element model with an acoustic cavity. We had 4 excitation subcases. So we had a road profile PSD, displacement at each tire patch, and then basically ran it over at a constant speed of 70 kph over a coarse chip seal road surface. The results were basically from a spectral domain and some attachment point FRFs, and it was basically exported out using Altair and VH Director. The physical data that was used was from an analog vehicle. We did 19 channels of acoustic and vibration data measured at the steering, at the seat, at the heel point, and at the driver's right and left ear. So model building, so from the CAE side, we needed to be able to take, and for the sake of everybody's consciousness, I'll kind of graze over this quickly. We were able to take the frequency-based source strength and transfer functions, combine them into a contribution that was in the frequency domain, and then basically convert that out to a time domain that we could then use as inputs into the MVH simulator. Now, in a little curveball that got thrown at me as I was working on this project, as we've shown in some previous slides, the shaker setup on the compact has excitation at the seat pad and the seat back. The CAE model that I was working with wasn't ideal, as I was only limited to acoustic, steering, and seat rail mounting point responses. So now I had to develop a method on how do I get this seat rail data into something that can be used in context at the seat. So again, I'm just going to kind of graze over this a little bit. We used the application of a transmissibility matrix. And basically what a transmissibility matrix is a over A transfer function matrix that basically can take acceleration at one point, transform it into acceleration at another point. And this can be derived from CAE, or it can be taken from just on-road data. In this case, that's what we ended up doing. We ended up taking a analog vehicle out on the road and using some seat pad accelerometers and some seat rail accelerometers, measured operating data, and then using some coded tools, converted that into a transmissibility matrix. Now, one interesting thing, and of course everybody realizes that, is an occupant's mass in that seated position is going to have a huge effect on the seat's physical vibration response. How the seat's going to vibrate with me sitting in it versus how the seat's going to vibrate when Dave is sitting in it is going to be completely different. So that has to be taken into consideration when we take these transmissibility measurements. So when we took the data, we basically took transmissibility data for a 80 kilogram male occupant and a 55 kilogram female occupant, and basically created 2 different test cases to be evaluated in the compact. Everything else from the supplemental vibration data for the steering and the seats and for the engine components was all taken from the analog model, while all of the seat pad, back, and pad vibration was done through this transmissibility approach. Okay, so here's the results. So we had several individuals sit in the operator position in the MVH compact and evaluate both the 80 kilogram male and 50 kilogram female transmissibility. What we saw was seat acceleration in the X and Y directions for the 55 kilogram occupant were 10 dB higher compared to the 80 kg. And in the Z direction, the 80 kg occupant was 10 dB higher. And that overall subjective performance could be felt while driving. So basically what we just created now was the ability to perceive the vibration in the seat using somebody else's build. So now you can personally evaluate what somebody with a bigger build or a smaller build could perceive inside the vehicle. So the benefits from some of this, we've got a multi-attribute MVH simulator that has the avenue to evaluate CAE simulation in context of the total vibroacoustic spectrum in the vehicle. And now with this approach of being able to use a seat rail to seat pad transmissibility transformation, the operator now has an opportunity to experience a vibroacoustic perception of different sized occupants, but also the ability to evaluate different seat designs in the compact. That's one of the big limiting factors that we find with the compact, is because we have the shakers mounted directly to the seat, we can't just put in any seat that we want. But now that we're able to use this type of transmissibility approach, if you've got CAE transmissibility data or on-road transmissibility data, you can use that and replicate virtually any seat in the compact. Conclusions, basically I'll kind of graze through this real quick. We have the models on the compact. I highly recommend giving it a try for yourself. The limiting factor with this is that the CAE model was only running at 1 speed, so you can only evaluate it at this 70 kph. But one of the next steps that we'd like to do is to be able to take our CAE model, evaluate it for several different speeds, and actually build a drivable model. So then you can basically have the full immersion and be able to fully experience that seat vibration from a different build occupant.
Thank you, Jeff, very much. Appreciate it.